Okay, this is exam 1 for physics 202 from spring 2010. In this first question it asks if the charge Q1 has a magnitude of 3 nanocoulombs, and it says magnitude. However, we know that because these lines are ending here, that it's minus 3 nanocoulombs. But what is the charge on Q2? You just count the lines. There are 6 lines going into the 3 nanocoulomb charge, and then there are 18 lines coming out of the Q2, so that means that Q2 is 3 times the charge of Q1, and it's positive because the lines are coming out, so that's 3 times 3 is 9, that's B. Consider 2 separate arrangements of insulating materials. If Q3 has a negative charge, what is the charge on Q1? Well, if this is negative, this has to be positive, so this is positive, so this has to be positive. 2 charges experience an electric force of 20 newtons. If the distance between the charges is doubled, what's the new force on the charge? Well, F is K QQ over R squared. If you double R, that gives you a factor of 4. So the force was originally 20. Now we take 1/4 of that, so it's 5 newtons. Consider these 2 charges. Where on the x-axis can a third positive charge be placed such that the net force on that charge is 0? Well, if we put a positive charge here, it experiences force towards the negative charge and away from that positive charge. So that's not an option. If we put it here, we get a force towards the minus Q charge, and then we get a force that's away from the plus Q charge. It's away from, and it's bigger because it's closer to the 3Q charge, which has a larger magnitude. However, if we put it over here, plus Q charge, it's attracted to the minus Q charge and repelled from the plus 3Q charge, but because it's further away from the 3Q charge, the 3Q charge affects it less. So the magnitude of the force is less than if it were on the right side of 3Q. So the answer is to the left of the minus Q charge, and that is A. Which of these is not an allowable charge? Option C represents 1.5 protons. And you can't have half of a proton. Which of these vectors best represents the direction of the electric field at the point P? Well, the electric field due to this charge is in this direction, and the electric field due to this charge is in this direction, and it's twice the magnitude of the first electric field vector. And you add these 2 vectors, and you would get the vector D. In this figure, an electron sits between 2 charged plates. The electron moves to the right in response to the electric field. What is the direction of the electric field? The electric field has to be to the left because a negative particle feels a force in the opposite direction of the electric field. Alright, so that is option D. Capacitor is hooked up to a battery with a voltage of 12 volts. After charging the capacitor, the battery is removed. What is the voltage across the capacitor if the area of the plates is doubled? Well, capacitance is equal to epsilon naught A over D. So if we double the area, that doubles the capacitance. Now when you hook it up to this battery of 12 volts, it puts a certain amount of charge on that capacitor, Q, and Q is equal to CV. Now once you remove the battery, that charge remains constant, so it keeps that charge. However, if you increase the capacitance, then that decreases the voltage, and you're increasing the capacitance by a factor of 2, so that's going to decrease your voltage by a factor of 1/2. So that would be C, or 6 volts. These 6 charges are in the corner of an equilateral hexagon. What pair of statements best describes the field and the potential at the center? Well, the first thing we want to consider the potential. We just count up the charges. This point is equidistant from all the charges, so we have to have equal numbers of positive and negative charges in order to have 0 potential. We have 1 negative, 2 negative charges, and 4 positive charges. So that means that the potential is not equal to 0. In fact, we could go further and say that it's greater than 0 because there are more positive charges than negative charges. Now for the electric field, we want to draw the vectors. I'm going to start up here and go clockwise and just draw the vectors for the electric field due to each charge. Due to this charge, the one on the top, the electric field is down. Due to this charge, the electric field is in this direction. Due to this charge, it's in this direction. Due to this charge, it's away. Due to this charge, it's towards. And due to this charge, it's away. Now, since all these charges have the same magnitude, all the electric fields and the distance to each charge is the same, all these electric fields are the same, so they all cancel out. So the electric field is equal to 0. So for number 9, the option is D. The following graph for potential versus position. If a proton is released at x equal a, what direction will it move? So you have a proton at this point, and we know that a proton wants to move from high to low potential. Alright, however, at this point, if it moves to the right, that's moving from low to high, and similarly, if it moves to the left, that's moving from low to high potential. So it's just going to stay right where it is. It's in a potential well, as we call it, and it won't move. It will be stationary. This is one way to isolate charged particles, is to create a potential well so that they can't move, because they don't want to move from low to high. They want to move from high to low. What is the voltage across the circle capacitor in this figure? Should have been able to do this fairly quickly. These two capacitors combine to give you an equivalent of 2 microfarad. So you could replace this circuit with two 2 microfarad capacitors. And since they're the same, then they both carry 5 volts. So the equivalent of these 2 capacitors has a 5 volt potential, and since these are in parallel, they both have 5 volts as well. So the answer is A, 5 volts. 2 wires A and B are made of the same material and have equal length, but the resistance of wire A is 4 times the resistance of wire B. How do their diameters compare? This is just like the concept test. So if the resistance of A is bigger than the resistance of B, that means that the diameter of A is less than the diameter of B. So we can automatically get rid of these 3. Now, resistance is equal to rho L over A, so our area is going to come into play, but area is proportional to diameter squared. So if we take half the diameter, I'm going to replace this. This is somewhat proportional to rho L over D squared. So if we take half of our diameter here, then that gives us a factor of 4 over here and a factor of 4 over here. So the area of A is the diameter of A is 1/2 the diameter of B. Now the area of A is 1/4 that of B, but we're not asking about area, I'm asking about diameter, so this is number D. If this still confuses you, you should look back on the concept test and look at the explanation there a little more. Which of these has a greater resistance, an incandescent light bulb or a bathroom heater? Now you should have been able to determine that the power of the bathroom heater is greater than 60 watts. A bathroom heater carries a power of about 1,000 watts. Anytime you have a heating element, it's going to use a lot of power because it creates it needs a lot of electricity to create heat. So the bathroom heater has a much greater resistance or much greater power. However, we know that P is equal to V squared over R, and so we want to know which one has the greater resistance. That's one with the least power, because if R is big, P is small. So that would be the bulb, C. When you apply a potential of 3 volts to a particular electrical device, the current is 2 amps. When you apply 6 volts, the current is 3 amps. Is this device ohmic or non-ohmic? Well, for the first one, we get a current of 3 volts over 2 amps. That's a resistance of 3 volts over 2 amps. And for the second one, if it's ohmic, it should be the same. 6 volts over 3 amps. So that's 2 ohms. And this is 3/2 ohms. So since these are different, this is a non-ohmic device. It does not follow Ohm's law. Okay, number 15, getting into the free response. I showed you a function for the potential, and then I asked you to draw the function for the electric field as a function of x. We know that the electric field is equal to the negative of the partial derivative of V with respect to x, and this is the x component of the electric field. Similarly, the y component of the electric field is the partial with respect to y, the negative of that. And the partial derivative is just like any other derivative, it's just the slope. So I just really want to make a plot that has the slope. I'm going to label the slope for each of these. The slope of this section is 0, the slope of this section is +1, and the slope of this section is equal to -1. Now, the electric field is just going to be the negative of those slopes. So from 0 to 2 up to this point, our electric field is just 0. From 2 to 3 up to this point, that covers this section, our electric field is going to be -1. Alright, so my graph is going to look something like this, -1. And then from 3 out to 7, the slope of my graph is going to be +1. And so my electric field, or the slope is -1. But the electric field is the negative of the slope. That goes to +1. That's the answer. Alright, the potential due to an electric field is given in this function. An electron is at x equal 1, y equal 1. What is the magnitude and direction of the force on the electron due to the electric field? Well, first I need to find out what is my electric field. Ex is minus del v del x. And that's equal to the negative of y squared minus 3y. If I put in those values for x and y, I get plus 2. And Ey is minus del v del y. That's equal to negative 2xy minus 3x plus 4. And that's equal to negative 3. Now, to find my force, this is the I component, this is the J component. My force is just equal to Q times E. This is an electron, so my charge is minus 1.6 times 10 to the minus 19 coulombs. And then my electric field is 2I minus 3J, that's in newtons per coulomb. And so my force in vector notation is negative 3.2 times 10 to the minus 19 I plus 4.8 times 10 to the minus 19 J newtons. J. So if I was to draw this in vector form, my x component is negative, my y component is positive, so my vector is going to look like this. I want to find the magnitude of this vector, and I want to find out what is that angle theta. Well, the magnitude of the vector, just using Pythagorean theorem, that is the square root of this number squared plus the square root of this number squared, gives me a magnitude of 5.8 times 10 to the minus 19 newtons. And then for the angle theta, I just say the inverse tangent of y over x, the y component over the x component. We write that in. That's the inverse tangent. The inverse tangent of 4.8 over 3.2. The 10 to the minus 19s cancel, and that gives me an answer of 56 degrees. Notice that I didn't put in the negative on the x component, because I'm just trying to figure out what is the angle measured with respect to the negative x-axis. So this is 56 degrees above the negative x-axis. If you had put in that negative 3.2 instead of positive 3.2, you would have been calculating what is this angle, and I'll call it phi, and that would not have been incorrect, but not usually the way I do it either. So phi in this case is 180 minus 56, which is 124 degrees. Either one of those would have been correct. But I'm looking also for the descriptor here. So that's the answer, this and this. 3 2 microcoulomb charges are assembled in the following configuration. How much work does it take to assemble the configuration? Well, let's see. We'll call this particle 1, this particle 2, and this particle 3. To put in place particle 1, I'll call this W1 is equal to 0. Alright, the work is equal to Q times delta V, but if I'm just bringing in this first charge, there are no other charges to provide a change in potential. So delta V is equal to 0. So work 1 is equal to 0. And then to bring in the second charge, which is this one, is just Q2 times delta V, which is Q2 times K Q1 over R. So that's going to be if I put in the numbers, let's see, this is 2 times 10 to the minus 6, 9 times 10 to the 9th, 2 times 10 to the minus 6 over the distance, which is 1 meter. That's this distance, and that's equal to 0.036 joules. And then finally work 3 is Q3 times delta V, which is Q3 times K Q1 over R, I'll call this R1, plus K Q2 over R2. Now all the values are the same. R1 in this case is the distance from here to here, so I'm going to just write in R1 is equal to 1 meter, and then R2 is the distance to particle 2, and this is equal to the square root of 1 squared plus 1 squared, that's the square root of 2, which is 1.4 meters. So R2 is equal to 1.4. And then you put in this value, and it's 0.062 joules. Then you just add up these three values, and the total work is 0.098 joules. Now, to find the potential at this point, you just add up potentials due to these two charges. So the potential at the point of particle 3, I'll call it V3, is equal to kq1 over 1 meter, which is the distance, plus kq2 over 1.4 meters. Putting in values for k and q as they're given, you get 31,000 volts. Alright, consider this circuit and answer these things. First, let's find the equivalent capacitance. I like to draw pictures. The first thing I want to do is find the equivalent capacitance of this. 2 plus 3 is equal to 5. If I redraw this, then I get replace those two capacitors with a 5 microfarad capacitor. Likewise, I can go and replace these two 10 microfarad capacitors right here with a 1 over 10 plus 1 over 10. Let's see, that is 1 equal to 1 over 2 over 10, which is 1 over 1/5, which is 5. So I get a 5 microfarad capacitor there. So that's combined these two first into this 5, and then these two, which are in series, which is also 5, and then I still have the 20 microfarad. Now I can further simplify this. The two 5 microfarads simplify down to just 10 microfarads with 20, and then finally I can find the final equivalent resistance, which is 1 over 10 plus 1 over 20, which is equal to 6.7 microfarads. So that's the first answer, 6.7 microfarads. Let's see, I want to know the charge on C1. Let's see, charge on C1. Can't do that right now. I want to know, because you need to know, in order to find the charge on C1, that's just going to be Q1 is equal to C1 times V1, but we don't know what the potential is on C1, so we're going to come back. We know that the potential on C1 is the same as the potential on C2, and the same as the potential on the equivalent of these two capacitors. Let's see, what is the potential across C2? C2 is this capacitor, and the potential on that capacitor is the same as the potential on these capacitors, which is the same as the potential on this capacitor. So we just need to find that first. And then C3, let's see, I guess we're going to go all the way down to C5, so we can't really answer any of these until we get to C5. C5 is this capacitor, which is the same as this one. This is hooked up to a 100-volt battery. I know that these capacitors have the same charge, so I can figure out what is the charge on this capacitor, which is just equal to CV, and so that's 6.7 times 100, that's 670 microcoulombs. So that means that I also have a charge of 670 microcoulombs here and 670 microcoulombs here. So I want to know the voltage on this capacitor, which is C5, and so voltage is just Q over C. That's Q5 over C5. That is 670 over 20 gives me my voltage, which is 33.5 volts. So let's fill this in, 33.5 volts. Similarly, I can go ahead and write in the energy stored. This is 1/2 CV squared. Alright, this is C5, V5, both of which you know those numbers, so let's just put in numbers 0.011 joules. And then I can start to fill in these others that I didn't know before. So let's see. C3, which is this capacitor, actually let's see, C2, which is this capacitor, is going to have the same potential as this capacitor. So if we want to know the potential across this capacitor, it's just going to equal 100 minus the potential on the other capacitor, which is 33.5, and so that is 66.5 volts. Alright, so that's the voltage across this capacitor, which is the voltage across C2. So C2 is 66.5 volts. Alright, now once we know the voltage on C2, 66.5, we know that that same voltage is on C1, so we can answer this question, which is 66.5 times the capacitance, which is 2, and that gives us a charge, which is 133 microcoulombs. And then our final one is, what is the voltage across C3? Now we know both of these share 66.5. Alright, so they're also the same, so they split that 66.5 volts by 2, so that is 33.25 or 33.3 volts. Alright, there's a lot of steps and a lot of just thinking about how to break up these circuits, so if you still have trouble with this, then please come see me. Okay, and this one is fairly straightforward. 100 watt bulb operates at 120 volts. What is the resistance of the bulb? Say power is equal to V squared over R, and solve for R, that's V squared over P. That is 120 volts squared over 100 watts, which is 144 ohms. What is the current through the light bulb? Ohm's law, V equals IR. I is equal to V over R, and you know all these, 120 over 144. And that gives you the current, which is 0.83 amps. And then in 10 seconds, how much charge is traveled? Well, Q is equal to I times T. That's 0.83 amps times 10 seconds, which is 8.3 coulombs.